Hello students, today we are going to learn about operational amplifier. So basically what is an amplifier? Amplifier, it is used for amplifying any signal from one form to another. Maybe it's a weak signal, we need to amplify it. So it's an electronic circuit or device which will increase the amplitude of the signal. So the electronic circuit may be of the form, you know, the BJT, it's a 3-pin device, and you have a emitter, collector and base. If I'm connecting it to BJT can be used as an amplifier also. Okay. So in the common emitter configuration, BJT can be used as an amplifier, that you know, that you would have read earlier. So this is one such example of an amplifier circuit. So where we are going to amplify the input signal and you are going to measure at the output the amplified signal. Okay. So now here waveform is same. If you see, both the waveforms are same. Okay. So if I'm measuring a sound waveform, so I'm going to measure the sound waveform. So it is being measured and the amplitude is weak. So what I'm going to do is I'm going to give this signal to the amplifier circuit and I'll be getting this signal. If you see the shape of the signal, this is being same, only the amplitude is increased. Okay. So now this is amplified sound sample. This can be done with the help of amplifier circuit. Okay. So what is mean by an operational amplifier, otherwise said to be op amp? Okay. Historically, op amp was designed to perform mathematical operations such as addition, subtraction, integration, and differentiation. Hence, the name it is said to be operational amplifier. Okay. So operational amplifier, otherwise said to be op amp. Initially, it was built to do the mathematical operations such as addition, subtraction, integration, and differentiation. So we can classify this circuits. Generally, any circuits can be classified into digital circuits and linear or analog circuits. So we will be classifying those circuits, and namely your analog circuits, as small scale integrated circuit, large scale integrated circuit. So these are all chips. Okay. So this operational amplifier consists of transistor. Not only single transistor, you will be having many transistor that is built in a chip. So the chip area will be ranging from 16,000 mm square to from 1,600 mm square to 16,000 mm square. So way back from 1947 till 2000, you have different versions of your integrated circuit. So coming to the pin diagram of 741 operational amplifier, this is one set of operational amplifier, namely 741. You have many different operational amplifier. So this is the first version of operational amplifier with an 8-pin DIP or 8-pin IC. Okay, dual inline package is said to be DIP. So it is an 8-pin DIP. Before going in detail for the operational amplifier and operational amplifier of 741, I'll just go ahead with the background of operational amplifier. So this was originally invented in the year 1940, and as I said, it is used or it is first invented for to execute the mathematical operations in analog electronic calculating machines. And the size of the operational amplifier have been shrunken because of the invention later after the invention of the transistor. And they have made it as an integrated circuit, as I said, from SSI to GSI, meaning small scale integrated circuit, to giga scale integrated circuit, meaning the chip size of the operational amplifier can be made smaller and smaller. So huge variety of applications in operational amplifier, namely its low cost and ease of mass production makes them extremely popular. So this is the first version of operational amplifier that was available in 1940. In 1940, so this is gap slash OR model. So this is how the first operational amplifier was made. And later, after the invention of your integrated circuits, namely your IC, so you have like this. This is said to be DIP, meaning you can insert it in a breadboard or in any circuit. Hence, it is said to be dual inline package. Okay. So, what are all the semiconductors, meaning semiconductor manufacturing company that they are going to manufacture this operational amplifier. So in 1963, Fairchild made operational amplifier of 702, and later 709, 741, 748. And National Semiconductor made it as LM101, 101A, 107, and 324 in 1974, of which we are going to focus on 741 for Fairchild Semiconductor. Not only Fairchild, many different semiconductor companies made the 741. Okay, how will be the internal circuit of 741 operational amplifier? So you have this many number of transistors inside your operational amplifier. If you could see that, you have many number of operational, meaning BJT or the transistor uh, inside your operational amplifier circuitry. Okay, so you have two inputs, namely inverting and the non-inverting input and non-inverting input, and one output, and two power supply pins, plus Vs and minus Vs. Okay. So, how operational amplifier can be used as a multi-stage amplifier? So, operational amplifier, you have a differential amplifier stage, you have a high gain stage, and class B push-pull amplifier. Okay, class B push-pull amplifier. These are the different stage of a multi-stage amplifier circuit in an op-amp. So if you see this operational amplifier, pin diagram of operational amplifier 741, IC 741. So it's an 8-pin IC. You have a first pin is an offset null. You have a dot terminal here, meaning wherever the dot is placed in an IC, to the left side of it, that is pin number 1. So pin number 1 is offset null. 2 and 3 are said to be inputs, inverting input and non-inverting input. Inverting input, whatever input that is being given here will be inverted and amplified, and you'll be getting the output in pin number 6. And non-inverting, it is vice versa. And you will be having your power supply pin, meaning minus VCC and plus VCC in your 7th and 4th pin respectively. Output is in 6th pin, and the 8th pin, there is no connection. There are two offset null pins. Okay. So plus 5 and minus 5 is exactly 180-degree opposite with each other. Plus 5 is in phase. Minus 5 will be out of phase with respect to your input. So what is the input range that can be given and the output range that can be obtained is plus or minus 5 volt to plus or minus 22 volt. Okay. So this 741 can also be available as an 8-pin IC, 10-pin IC and 14-pin IC also. But what we see here is a 7-pin IC. Okay. So what are all the packages available? So it is dual inline package, JEP, TO package, and the PCB flat package, meaning and I mean you'll be soldering in a PCB thing, so you won't be getting a dip sort of thing. You'll be having a flat package here. Okay, right. So coming to the manufacturers, as we have already discussed, we have Fairchild, National Semiconductor. Similarly, you have Motorola, RCA, Texas, Signeting, Burr Brown, like that. You have many other manufacturers who are manufacturing this IC 741 or in general operational amplifier. So what are the different classes of IC? You have 741 IC, which is temperature dependent, and 741C. So if you see 741 IC, it is minus 55 degree to 125 degree centigrade, and the 74C, it is 0 to 70 degree centigrade. You have 741S and SC with higher slew rates, 741A and E with higher amplification rate. Like that, we have different classes of 741 ICs. So how will be your terminals? How will you represent an operational amplifier with a triangular symbol? And you have two inputs, second and third pin are said to be the inverting terminal and non-inverting terminal. And you have two power supply pins, fourth and the seventh pin. Fourth pin is for negative and seventh pin for the positive. And sixth pin is for your output pin. Okay. So for an ideal op amp, if two inverting and non-inverting terminal, the input terminal, if the voltage is V1 and V2 are the input voltages in your non-inverting and the inverting terminal. So the difference in voltage is said to be Vd. Okay, assume that initially V1 equal to V2, so Vd is equal to 0. For an ideal operational amplifier, the Vd has to be 0. There should not be any input current, namely your I1 should be 0 and I2 should be 0. And there are certain characteristics of an ideal amplifier. So what are they? Let us discuss here. So the ideal operational amplifier, if you see that the input impedance is infinite, because here meaning what does it mean? It's not because. So what does it mean? What is that input impedance is infinite? If any circuit is connected before this operational amplifier, they cannot load this op amp. They cannot load this op amp. Hence, it is said to be infinite impedance, input impedance. And AOL is said to be open loop gain. Open loop gain is infinite. This is all the characteristics for an ideal op amp. And output resistance R naught is equal to 0. Bandwidth of the operational amplifier, bandwidth, the range of frequencies with which this operational amplifier can be operated. The bandwidth is infinite. You have zero offset. There is no voltage. Your output voltage is 0 when V1 equal to V2 is equal to 0. Okay, because there is no differential potential, Vd is equal to 0. So you have 0 offset, you have 0 offset. So the current I1 equal to I2 is equal to 0, as I already discussed. So Ri is equal to infinity, because no any other input circuits can load your operational amplifier. Hence it is said to be Ri is infinite. Open loop impedance is, or open loop gain is infinite. And you have a finite output voltage, or for a finite input voltage, similarly your finite output voltage is also 0. And output impedance is, resistance or impedance is 0. So V naught is independent of the current drawn. Okay, V naught is independent of the current drawn. So how will you represent a practical operational amplifier? Okay. So the input side have a resistance. You have two input voltages V1 and V2 in the uh, inverting and the non-inverting terminals. And R is the input resistance. The difference in voltage is said to be Vd. Okay, that is in your input side. And the output side, so you have a dependent source because you have an open loop voltage gain, AOL, that is dependent on this differential voltage. Whatever that is we are feeding here, that will be amplified and you will be getting that as output. So V naught is nothing but AOL into Vd, and you have an output resistance. So this is your triangular symbol. Okay. So V naught is nothing but A naught L into Vd. So this is voltage controlled voltage source. This dependent source is voltage controlled voltage source. Okay. So V naught is nothing but A naught L into Vd. We can write it as V1 minus V2. So this is the op-amp equivalent circuit in a more neat way. And this is your V1, V2. The difference is V in. You have an input impedance of R in, and your input power supply voltages are plus Vs and minus Vs, and you have a dependent source, voltage control voltage source, and you have an R out here. Okay. So circuit symbol of operational amplifier, you have an inverting input and non-inverting input with a gain of A, you will be getting V, the output voltage. A is said to be large signal voltage gain. As we have discussed already, this is an 8-pin IC that we are going to discuss throughout this discussion. And it's an 8-pin IC with 1 and 5 being offset null to nullify any difference in input voltage or difference in output voltage we are getting. You need to supply some sort of voltage here in the null pin, and inverting and the non-inverting inputs, namely your 2 and the 3, and your power supply voltages are said to be plus 4 and plus 7, and there is no connection in the 8th pin. And you have input terminal, output terminal, and 7 is connected to positive and 4 is connected to negative. So ideal operational amplifier, your input impedance is infinite, your output impedance is zero, your voltage gain is infinite. But that is not in the case of practical operational amplifier. Input impedance in the range of mega ohms, output impedance in the range of ohms, and your voltage gain will be in the order of 10 power 5. And how will be the voltage transfer characteristics? For example, if I'm increasing the input voltage, my gain is proportionately, it is going to increase, and it is linear for certain point of time. After that, when it reaches your input supply voltage, it will reach the saturation level. That happens in the negative side as well. The slope is equal to A into Vd. So this is the range of the amplifier where we operate the operational amplifier. Okay. So coming to the applications, the first thing is non-inverting amplifier. So as the name says, non-inverting amplifier. So input is given here in the non-inverting terminal, meaning the plus terminal, meaning input, if I'm giving V in, output will also be positive since I'm giving the input in the positive terminal. So more about the derivations, I'll just tell you now. So non-inverting operational amplifier, I'm going to give the input at the positive terminal. VA is connected to the positive terminal, and to the negative terminal. The negative terminal is grounded. You have a resistance of R1. You have a feedback resistance of RF that is connected between your R1 and your output terminal. And if I'm taking this as V1, I'm going to take this as V2. Okay, this as V2, and see, this is virtually grounded. If I'm telling this is V1, which is nothing but V1 is Vi, this should also be Vi, V2 should also be Vi. Let me take the node as A, okay, and it is being grounded, so V naught equal to V in, that is in phase, V naught equal to V in phase, okay, that is your V naught equal to V in, both are same. So V naught equal to V in. So the difference in voltage is nothing but V1 minus V2, that is generally named as Vd, that should be equal to 0 because both are Va. This is also Va, this is also Va. Okay. So what is VA? VA is nothing but the voltage across this node potential. Node potential is VI, which is nothing but mentioned here. VA is equal to VI. VA is equal to VI. Okay. Is it okay? Right. So how will you write your input voltage VI? Input voltage VI is nothing but, okay, if you look at this circuit, these two resistances are in series, R1 plus R. Okay, R1 plus R. I need what is the voltage across your R1, that is your input voltage. Here, okay, here, okay. So how will I write? VI is nothing but V naught, okay, V naught into R1 divided by R1 plus R. Simple voltage division rule. It's a closed circuit. Is it okay? The total voltage, if I need to know about this VI, if I'm having the total voltage V naught into this particular resistance, I know V naught into this particular resistance, V naught into R1 divided by R1 plus R. That's all. Okay. So this is your non-inverting terminal. This is your non-inverting input voltage. So then if I bring this V naught by Vi, meaning gain, in terms of gain, V naught by Vi is nothing but R1 plus Rf divided by R1, which is equal to 1 plus Rf by R1. So the closed loop gain is nothing but 1 plus Rf by Ri, which is equal to V naught by Vi in case of non-inverting operational amplifier. So in case of inverting operational amplifier, if you look here, your inverting operational amplifier, you will be giving input in the inverting terminal, meaning Vi is given in the negative terminal. Okay, all other things are same. R1 is the input resistance, RF is the feedback resistance, and non-inverting terminal is grounded. Okay, so if I want to write I1, which is nothing but the current flowing through R1 and RF, which is nothing but Vi divided by R1. Okay, Vi by R1, that is the first equation, and we know already Vd is nothing but V1 minus V2. Okay, and coming here, this is your output terminal. V0 is nothing but minus of I1 into RF. This is said to be inverting an operational amplifier, or output will be negative. Whatever input that we are giving, that is going to be inverted. Okay. So V0 is nothing but minus I1 into RF. I1 I can write it as Vi by R1. So minus Vi by R1 into RF. So gain V0 by Vi is nothing but minus of RF by R1. It is nothing but your closed loop gain of an inverting amplifier. Okay. So now in terms of impedance, if I'm going to write the same closed loop gain, instead of resistance, I'll be writing it in Z, ZF by ZF. So let us take a simple problem in case of this inverting operational amplifier. Being R1 is 5K and RF is 10K and RL is 10K. Okay. So the load current is this, the I0 is this, input current I1. Okay, Vi is said to be 1 volt. Okay, if Vi is said to be in 1 volt, calculate your I1, V0, I1, and the IL are the total current. We know I1. I1 is nothing but the current flowing through R1, which is nothing but Vi by R1. So Vi by R1. And similarly, your output voltage V0. V0 is nothing but minus Vi into. So from this gain formula, you can rearrange. If I need V0, so minus ZF by Zi into Vi. That is what here I have written, but in terms of resistances. And IL is nothing but the current flowing through this 10K, which is nothing but V0 by RL. Okay, the total current is nothing but you have your I1 and IL, only two currents. So I1 plus IL, which is nothing but I0. Okay, so that is how you will be calculating all this. So how will you represent a practical inverting operational amplifier? So you will be giving an input voltage Ri, differential voltage is applied across Ri. You have a feedback resistance RF, and you have an open loop voltage gain or a dependent source with open loop voltage gain R0 and V0. Okay. So R equivalent is nothing but R1 parallel, both are parallel because here you have an RF. So R1 parallel Ri. Okay. So approximately we'll be taking R equivalent should be equal to 1. Mostly Ri will be greater than R1. Okay. So V equivalent is nothing but input voltage. R equivalent is nothing but your input resistance. So from the loop we can write here, from the loop we can write it as V0 from the output loop, not from the input loop. So here from the output loop, V0 is nothing but, okay. So I into R0 plus A0 L into Vd. So Vd is nothing but V0 minus I R0 by AOL. Okay. And again, if I write Vd plus IRF, here I can write, I'm sorry. So here I can write Vd plus IRF, okay, plus V0. Vd plus IRF plus V0 from the input side. This is Vd, okay. This is IRF and this is V0. When I want to write the voltage that is being involved in the resistance RF, okay. So use this 3 into, so you'll be getting V0 into 1 plus AOL equal to I into R0 minus AOL into RF. Okay. So KVL around the loop, Vi is equal to the first loop, namely your input loop. So Vi R1 into I, and then you have Ri. So Vi is equal to I into R1 plus RF. Both the resistance are there, plus V0. Okay. So from here, calculate your I, equation number 5, and substitute this I here in equation number 6. So you'll be getting the closed loop gain to be V0 by Vn for a practical operational amplifier, R0 minus A0 L into RF divided by R0 plus RF plus R1 into 1 plus A0. Okay. So this is equation number 7. So if AOL is greater than 1 and AOL into R1 is greater than R0 plus RF, so you will be getting the ideal operational amplifier case minus RF by RI. Okay. So the input resistance, how will you calculate? V equivalent is nothing but VI RI, the total impedance. This is your input. So VI RI divided by the total thing is R1 plus RI. That is your input impedance. Okay. So RIF is nothing but VD by I. So input impedance can also be written as RF plus R0 divided by 1 plus A0. So this much in detail we are not going to read, only the basic ideal operational amplifier is enough. So if you go ahead with the equation of closed loop gain, which is nothing but minus RF divided by RI, and then the closed loop gain for the non-inverting operational amplifier, which is nothing but 1 plus RF by RI. This is enough. With this, we will solve one problem. Okay. I hope you can understand whatever I have taught today. We will see a problem and the different amplification like a summing amplifier, differential amplifier, and subtractor in the next class. Thank you.